Hello, I'm Maurya Reddy. I'm going to explain about the phase about the phase two of the science project. Here, my assigned molecule is one AIE underscore A dot PDB. In phase one, we our aim is to generate the input files required for the simulations and run the assembly simulations of that given protein using NEMD. Here is the attached. I have attached the procedure for generation of input files and the NEMD simulation also, and I have attached the drive link for all my files and the videos regarding the phase one of the project. And here I have mentioned the which files are useful for which one, which files are which files are going to describe our project. Now I'm telling. Now I'm going to discuss about the phase two of our science two project. Our aim is just calculating the PMF and the work calculations. And here it is my attached drive link. So now for the phase two, like we need to discuss about the Jarzynski equality. The Jarzynski equality is an equation in statistical mechanics that relates free energy differences between two states and the irreversible work along an ensemble of trajectories joining the same states. It is named after the physicist Christopher Jarzynski. In thermodynamics, the free energy difference delta F equal to Fa minus Fe between two states A and B is connected to the work done W on the system through the inequality, that is delta F is less than or equal to W, with equality holding in the case of a quasi-static process. That is like one system can be taken from state A to state B like very slowly, like infinitely slowly means very slowly. The equation is derived from the other theorem called this equality is derived from the other theorem called Crookes fluctuation theorem, which is an equation in statistical mechanics that relates the work done of the system during a non-equilibrium transformation to the free energy difference between initial and final state of the transformation. The equality is as follows. Here equality is like e power minus delta f by kt, and that is equal to e power minus w by kt bar. Here bar defines the average work done over all trajectories. So the equality is exponential of minus of f of c of t minus f of c of 0 by t equal to exponential of minus of w of t by capital T. For reversible problem, the equality holds, otherwise the right hand side value will be larger than the left hand side value. It does not hold for a reversible process. Upon simplifying, we can write above equation as f like f of c of t minus f of c of 0 equal to minus t log of, like we are just taking the log of there, f of c of t minus f of c of 0 equal to w of t minus 1 by 2 to this the expansion of the logarithmic expansion. The terms in the right hand RHS are called like that is W of t and W of t whole square W of t. Those are called, this is the second order cumulative. So now the PMF estimation is done using these three different forms. F exponential is equal to minus t log of exponential of W of t by t. This is the exact equation we have discussed above. So now if we consider only this first order cumulative, the F1 equal to the average of W of t and F2 equal to W of t minus 1 by 2. So this script is we have taken this script for the calculation of PMF estimations, and we have this called cumulants.tcl. Finally, all those three estimates we have plotted all these estimates in a single graph. So the steps we followed to generate our graphs here. So so the new trajectories are created by setting V to 0.0002 a per time step in assembly.tcl file. That will be in some last line, I think. In assembly.nemd file, I took time step as 0.fs per step and ran 10 lakh times. Each trajectory is present in da underscore assembly underscore tcl dot out file. So after doing all this, we'll run the command dot slash nemd to smd.nemd, and we'll redirect that output to this da underscore assembly dot log file. The log file should contain exactly 20,001 lines. Actually, I didn't get those 20,001 lines in the primary iteration, so I have been trying to get those 20,000 lines. So copied we we just copied that log file to some trash1.route file and ran the same command more times and stored the results in two files, that is dash2.out and dash3.out. And I have attached these three files including log file in the my drive link. For making da.dat, the files were combined using Excel and a tab delimited. Dot .dat file was made using the first column as a time and second to fifth as a trajectory distance and sixth to eighth column as force applied. The code is present in the makedata.py. I have attached that Python file also in my Google Drive. So for loading this trajectory into VMD, load hyphen traject.tcl script was used into VMD. The load hyphen traject.tcl script was used, and the row numbers ranged from 1 to 20,001. The script has three variables: T is the time step, 20,001 rows, and Z is 20,001 into 3 matrix which contains end-to-end distance, and F is 20,001 into 3 matrix which contains 4 trajectories. The first plot was made using plot extension time.tcl with time on x-axis and extension on y-axis. Here we fix first atom in TCL file, fixed and last atom is pulled with some force and velocity. The values are same as that of used in phase 1. The second plot was made using plot force extension.tcl, which has plot for force extension. For work calculation, we run following commands in TK console of VMD. Like we are setting this time step to 0.1 and V to 0.01, set T to 0.6. Here T Boltzmann constant equal temperature equal to. So now set C, the we define this empty array C is defined to just store the distance between two constant points. And I have set I as 35.32 as initial constant distance. Like I just want to differentiate between. I just want to differentiate from all of them. Uh, so now we will be running array loop to for filling the array C and updating using Newton's equations of motion, that is distance equal to initial position plus velocity, u equal s equal to u plus, so initial position plus velocity Newton. Yeah, it's not it's constant velocity. So work done is calculated using script calwork.to.tcl and plot is made using plot w.tcl. So I just want to differentiate the graph between me and my other friends. So my molecule is 1A IE underscore A dot PDB, and my other friend Datta's molecule is 1JJO underscore E dot PDB, and Vasisht is 4H6S underscore A dot PDB. So the first plot is like extension versus time plot. The time is on x-axis and extension is on y-axis. It it quite linearly to the time the extension will be varying. The difference occurred here is like, so we the difference here is like me and Datta got the extension values at 12.5 starting, like Vasish got at minus 35. So the graph is varying linear quietly. That is the only difference between our three plots. The graph is varying linearly for extension versus time plot. Now the force versus extension, we have done force versus extension plot also. Like extension is on x-axis and force is on y-axis. The graph varies linearly, but it fluctuates. Like varies linear, but it always fluctuates on a certain line. Like this is my graph, and this is Datta's, and this is versus. So now work versus like we have done the work versus extension plot also. The graph varies exponentially here. So here I have taken extension on x-axis and work on y-axis. So it's approximately varying exponentially. And this is Datta and this is Vasish's. So now PMF. So it decreases exponentially for F2, whereas for F1 and Fx it increases almost linearly. This is F2 and F1 and Fxp, it increases almost linearly. This is for me, and similar thing happened to Datta also, and Vasisht is quite different. Like they are increasing linearly, but this was decreasing more exponentially. It was increasing linearly, like it was it was increasing more than us. So